Hello everyone, this is my Physics 2211 Lab 1 video over constant velocity. The purpose of this lab was to apply Newton's second law of motion to an object moving with a constant velocity and compare it to an ideal computer model to demonstrate the momentum principle. With no net forces acting on either of them, the position should stay the same for both the computational model and the real object. This assumed that there was no friction or drag acting against the moving cart and that the net force was 0 newtons. Overall, this experiment showed that the computer model, assuming no force acted on the moving cart, overestimated the position, getting worse over time, and this is likely due to the real object having friction and drag affecting it. So the fundamentals for this lab include Newton's second law of motion, which is given by the formula the net force equals the change in momentum over the change in time, or mass times acceleration. The change in momentum depends on the net force acting on the object, but since there is no force, this means that there will be no change in velocity. This can also be seen by the velocity update formula, which can be derived from Newton's second law of motion. And if you look at this, if you change the net force to 0, the right side will cancel out and leave you with just velocity final equals velocity initial. Additionally, the position update formula is important to help calculate where the cart will be at different times. And since the force is constant, V average can be found as V initial plus V final divided by 2. In this experiment, the system consisted of the rolling cart, while the surroundings were the track, the earth, and our hands when we pushed the cart initially. The cart was pushed along the track and a video was taken of it after the initial push stopped, and the software tracker was used to track the position of the cart at different time points, and GlowScript was used to create a computer model of the cart's motion so that they could be compared to each other. A graph comparing the experimental position found with tracker and the model position using GlowScript was made to compare the two. The motion of the cart was measured from a distance of 0.2 meters to 0.8 meters from the start of the track because this is when the applied force was first removed to push the cart and to when the cart leaves the frame. The initial conditions were that the position was 0.0009966 meters for the experiment and the model, and the initial velocity was found by finding the change in position uh, divided by change in time after the first time step, which is shown in this equation here. And it was only for the x direction since we are not modeling movement in the y direction. Time was measured every 0.033 seconds since the frame rate was 30 frames per second. This was the tracker video being used, and the position was taken from the bottom left corner of the cart. The computational model used a mass of the cart of approximately 1.5 kilograms, but this doesn't affect motion since the force is 0, so it doesn't matter. The initial conditions, including the position and velocity vectors from tracker, were put in, and the delta t was set to 1/30th of a second since the video frame rate was 30 frames per second. The while loop that was in charge of running the computational model was looped for 1.7 seconds since this is how long that the cart moved. And the velocity update and position update formulas were entered in to apply the momentum principle. After this computational model was run, a graph of the position versus time for both the experiment and the model was plotted, and as you can see, the model starts pretty close but starts to deviate from it and overestimate the position. This is likely because the experimental model will slow down due to there being some friction that we did not account for. The errors in this lab include the assumption that no forces acted on the cart, even though we know that friction and drag likely slowed down the cart. Additionally, the position of the tracker software used a video that was kind of blurry at parts, so it was hard to use the same point throughout. For the discussion, we're going to talk about two questions. What if the axes were flipped as first? How would the results change then? So, since the vertical movement wasn't measured, there would be no effect on flipping the y-axis. But for the x-axis, the positive direction was set to the right since that is the direction that the object moved. So flipping the axis would not have changed anything significant about the data except for the fact that the slope would then be negative and going down instead of positive and going up as we saw before. But the overall results would be the same since the magnitude of the displacement wouldn't change. Second, what do the observations mean, and how many forces were added to give the net force of 0 if that can be calculated? Well, the experimental model having less velocity and smaller displacement at the end compared to the computational model shows that the net force was not 0 because the experimental model started to slow down. Therefore, it cannot be determined how many forces there were added together to cause this motion, and the net force was not zero. But we do know that there was likely the gravitational force and the normal force to add to zero in the vertical component, and likely friction and drag led to a negative force in the x direction, causing it to slow down. And that is all.